So welcome to the lecture on state space method. In this lecture we will discuss a problem related to controller design and about controllability. So we discuss this problem that we are given a plant that is gs equal to 20s plus 5 upon s plus 1 s plus 4, and we have to design the phase variable feedback gains to yield 9.5% overshoot and a settling time of 0.74 second. So we were discussing that we have this transfer function gs, and we have, this is the characteristic equation. So we have this equation that is s cube plus 5s square plus 4s equal to 0. Now we can write this as s cube, we can compare, plus a2 s square plus a1 s plus a0 equal to 0. So if we compare this, we will find the coefficients of this a1, a2, a0. So here a2 equal to 5, a1 equal to 4 and a0 equal to 0. So we have the system. If we represent this system in the state space, we can write x dot equal to 0 1 0 0 1 0 sorry 0 0 1, and here we can write reverse order with negative sign. So this is 0 and this is minus a1, so minus 4, and this is minus a2, so minus 5. This is matrix A. So AX plus B so B matrix we have 0 0 1 and U, and here y equal to, so y matrix come from here, so 100 20 and 0, and here x. So we know that C matrix we can write this by these coefficients. Now if we write A minus BK matrix, so A minus BK, because we assume that there are, so there are three coefficients A1, A2 and A0. So we need three k values, so k equal to k1, k2 and k3. So here we have k, so here we have k that is equal to k1, k2, k3. Now this matrix we can write, so A minus BK, so we can write this as equal to, so this is 3 by 3 matrix, so 0 1 0 0 0 1, and this will be minus, so here we will have k3, sorry k1 minus k1, because here it is minus a0 plus k1, so a0 is 0, so it is minus k1 minus a1 plus k2, so 4 plus k2 and minus 5 plus k3. So this is A minus BK. Now the characteristic equation, that is this, will be changed. So it is like s cube plus, now here we will have 5 plus k3 s square plus 4 plus k2 s plus k1, that is equal to 0. This is the new characteristic equation. Now what is the design requirement? This is the design requirement. So we have got two equations. This is the first equation and this is the second equation. So this is the initial system and this is a system we want. So we want the values of k1, k2, k3. Okay, so we have to select k1, k2, k3 to obtain what objective? This objective. So here we have Ts equal to 0.74. So we know that here Ts equal to 4 upon sigma d or zeta omega n, sigma d or 4 upon zeta omega n. So that is 0.74. So we can find sigma d equal to 5.4 or zeta omega n equal to 5.4. Now we have percentage overshoot, we have to find the damping. So damping is equal to we have, if we are given percent overshoot, we can find the damping from here and we have percent overshoot 9.5. So we put 9.5 and we will get the value of damping equal to 0.6. And here this is zeta omega n, so here we can also find omega n. And omega d equal to omega n root 1 minus zeta square, and omega n equal to sigma d upon damping, that is 0.6 into root 1 minus 0.6 square. So we get omega d equal to 7.2. So now we obtain that we have this sigma d equal to 5.4 and omega d equal to 7.2. It means we, to obtain 9.5% overshoot and damping equal to so that equivalent to damping equal to 0.6 and settling time equal to 0.74, we need to put the poles at this real part and this imaginary part. So we want to put these poles here somewhere, so that we have, this is omega d and this is sigma d, omega d into j. So we have 5.4 plus minus j 7.2. So these are the two poles where the two poles, because this system has s cube, so there are total 3 poles. So out of 3, the 2 poles, complex poles, should be this. So we have here, let's say s1 and 2 equal to this. Now what about s3? So the third pole, where should I put? So we know that here we have GS equal to S 20 S plus 5 upon this system, that is so the 0 is at 5. So if we put the third pole near to this 0, the pole 0 cancellation will take place, and therefore the higher order pole will not affect the response of the dominant poles. So therefore let's put this third pole at near 5. So let's say 5.1. So now what should be the resulting equation? We have S minus sigma 1 into S minus sigma 2 into S minus sigma 3 equal to 0. So this should be the characteristic equation. If we have 3 poles, so S minus 5.4 plus J 7.2, S minus 5.4 minus J 7.2, and here S minus 5.1. So this is the characteristic equation. This is the desired characteristic equation, because these are the desired pole locations. So now if we solve this equation, we will obtain this equation as, so we can have S minus 5.4 minus J 7.2, and this is S minus 5.4 plus J plus J 7.2, and this is S minus 5.1 equal to 0. So this we can write S minus 5.4 square and minus J 7.2 square into S minus 5.1, that is equal to 0. And so here we can obtain this as S square plus 10.8 S plus 81 into S. So sorry, this is plus, because here this is minus 1. We are putting at negative side, because here the 0 is at S equal to minus 5. So this S3 is minus 5.1. So we have here S minus minus 5.1. So it is plus. So S plus 5.1, that is equal to 0. So we finally obtain this as S cube plus 15.9 S square plus 136.08 S plus 413.1 equal to 0. So this is equation number 3, let's say. Now this is the desired characteristic equation, because that will put the poles at these locations, and this is also the desired characteristic equation that will set these values of K1, K2, K3 to put the poles at the desired location. So these two equations can be compared, and we can find the values of K1, required values of K1, K2, K3. that will put these poles, put the system at these locations. So we compare these coefficients. So here if we compare s square, so 5 plus k3 equal to 15.9 and 4 plus k2 equal to 136.08 and k1 equal to 413.1. So from here we can obtain that k3 equal to 10.9. From here we can obtain k2 equal to 132.08 and the k1 equal to 413.1. And here we have the 0 is the same. So now what is the new system? So here the new equation is x dot equal to a x, so 0 1 0 0 0 1, and here we have so minus 413.1 minus 136.08 and minus 15.9 into x plus 001 u and y equal to c x and the transfer function, because this is the characteristic equation, we can write transfer function. So transfer function is 20s plus 5 upon, here we have, this is the characteristic equation, so we can write s cube plus 15.9 s square plus 136.08 s plus 413.1. So these are the systems. So this is in the state space, we have obtained this system, and we have obtained the values of feedback gains, that will be feedback, and they will put all the 3 poles at desired location. So here we have taken this third pole at minus 5.1. We can also select this value maybe very higher, so we can put this pole at very far from the dominant real part of the dominant pole, maybe at S3 equal to 30 or 50, and we can find the value of gains that will corresponding this value. So we can put the poles, all these system poles at the desired locations. Here we applied the pole 0 cancellation, but here we could say that the a condition that the pole, third pole is very far, so it is not affecting much to the dominant pole's response. And this is the transfer function. So the system is the same. We have 2 different representation. One is the transfer function, that is the frequency domain approach, and this is the time domain approach, that is state space. So now we have discussed for these systems how to find this. So now we will discuss the concept of controllability. So when we define the state variables, so we said that the state variable is takes the system from one state to other when we apply some input or initial conditions. So if an input to a system takes every state variable from a desired initial state to some desired final state, then the system is said to be controllable. If there is no effect of input on any state variable, means if we are giving input but the state variable is not affected or it is not changed, so it means the system is uncontrollable. Therefore, to control the pole location, because we were trying to place the poles at desired location, so if we want to do this, we are controlling the pole location of the closed loop system by giving some input u or giving some feedback gain as an input. So if we say that the control signal u, we want to, through this control signal u, we want to control the pole location so that we can control the behavior of each state variable in X. If any of the state variable cannot be controlled by u, then we cannot place the poles of the system where we desire. So for example, let's take some system, like suppose we have this system x dot equal to minus a1 0 0 0 minus a2 0 0 0 minus a3 x plus 1 1 1 u. Now what is this system? So if let's say here we write this x1 x2 x3, so here we can write x1 dot equal to minus a1 x1 plus u. Here we can write x2 dot, because here it is x1 dot x2 dot and x3 dot. So here x2 dot we can write minus a2 x2 plus u, then x3 dot equal to minus a3 x3 plus u. So here we see that if we are giving the input, we are getting the state variable is affected by this input because they are function of u. So here we can say that the system is controllable because each state variable is getting affected and by the input u. Now we take another system, let's say x dot equal to minus a4 0 0 0 minus a5 0 0 0 minus a6, and here we have 0 1 1 and here is u. Now if we want to write this equation, we can write x1 dot equal to minus a4 x1, x2 dot equal to minus a5 x2 plus u, and x3 dot equal to minus a6 x3 plus u. So here we see that this state variable is not affected from the input. So x1 is not controlled by input u, and therefore this state variable is not affected by u, and so the system is uncontrollable. So here we see that this system is have distinct eigenvalues because that is a diagonal element, so the eigenvalues are distinct, and so we can say that a system with distinct eigenvalues and a diagonal system matrix is controllable if the input coupling matrix B does not have any rows that are 0. So if we have this kind of system, diagonal system, we have, if any row of this B matrix, because this is B, so B matrix is 0, then the system is uncontrollable. However, if we have the repetitive poles, then if the system has multiple poles, it doesn't have distinct poles, then how to find the controllability of a system? So there the controllability is defined. So to find controllability of such a system, we have to find the controllability matrix. So we call it controllability matrix CM. And CM equal to B AB A square B and here it is A n minus 1 B. And if the system is of nth order, so if our matrix A is n by n matrix, so our system is of nth order, so the rank of Cm equal to n, so it is controllable. Otherwise it is, if it is not equal to n, then it is uncontrollable. So for any system we can use this method to find the controllability. So first we calculate the controllability matrix. So let's take one example. So if we have a system like x dot equal to minus 1 1 0 0 minus 1 0 0 0 minus 2, x plus 0 1 1 u. Now we can see that here are multiple poles at minus 1. So now we calculate the Cm. So we have to calculate the Cm. So this we have to calculate. So here B is, now we complete this. So B is this. So this is A, that is 3 by 3. So A, and this is B. So here we have B 0 1 1. Now we calculate AB. So A into B we can calculate. So we multiply this A matrix to B matrix, and we will get 1 minus 1 minus 2. And when we calculate A square B, we have to first calculate A into A, and then we calculate this into B, so we can get A square B. So A square B we calculate, we will get minus 2 1 4. So determinant this Cm equal to -1, and this rank is 3 because this is its rank is 3, and that is equal to the order of the system, that is n. So this is controllable matrix. So here just by seeing this row we can't say, because here the first row of the B matrix was 0, but the system is controllable. So the examples discussed in this lecture were taken from the book of Norman S. Nice, Control Systems Engineering. So I thank you for attending this lecture, and let's see in the next lecture. Thank you.